Long before the black box, before any recorder, a train wreck had only one witness: the wreckage itself. Twisted steel, fractured iron, the resting angle of every carriage. This is how engineers read a disaster backwards, recreating historic train accidents. A crash is a story told in reverse. The investigator starts at the end, the debris, the bodies, the one broken component, and works back through physics, metallurgy, and signaling logs to the first small flaw. For disasters across 120 years, each hiding its own lesson. James Reason called it the Swiss cheese model. Every safety layer, material, brake, signal, structure, is a slice with holes in it. Most days the holes don't align, and the hazard is stopped by the next slice. Catastrophe comes only when every hole lines up and the danger passes clean through. Our 4 cases sit along that idea. 1879, a bridge in a storm. 1889, a runaway on a hill. 1998, a wheel at speed. 1999, a signal in the sun. Different centuries, the same anatomy of failure. The night of the 28th of December, 1879. A storm battered the Firth of Tay, Beaufort force 10 to 12, lateral gusts near 80 miles an hour. A North British Railway train rolled onto the central high girders. The spans gave way, and the train and all 59 souls confirmed aboard fell into the black water. No survivors. Why did it fall? Reconstruct the forces. Wind pushes sideways against the tall lattice piers. Windward columns in tension and lift, leeward in compression and buckling, held together only by thin diagonal cross-bracing. Yet the designer, Sir Thomas Bouch, had made no explicit allowance for lateral wind pressure at all. Period engineers used the Smeaton formula P equals 0.005 times V squared. Pressure in pounds per square foot from wind speed in miles per hour. At 80 miles an hour, that's about 32 pounds per square foot, and forensic work by Henry Law and William Barlow showed the real load on the truss girders was higher still. The columns were brittle gray cast iron, cast horizontally, anchored to cast lugs with tapered, cast bolt holes, not drilled, concentrating the load onto a knife edge. 2 years of traffic had flexed those lugs with every passing train, cyclic fatigue on brittle metal. In the storm, the windward columns lifted, the tie bars snapped tight, and the lug sheared clean. The Wind Pressure Commission answered with the first mandatory wind load standard, a minimum of 56 pounds per square foot, and banned brittle cast iron from the key members of high railway bridges, forcing the shift to steel and ductile wrought iron. The 12th of June, 1889. A Sunday school excursion, 15 crowded carriages, hundreds of children, stalled on a 1 in 75 gradient near Armagh. The crew uncoupled the rear 10 carriages to take the front 5 ahead. The engine rolled back a fraction as it restarted, and that jolt broke the rear portion free. It ran backward downhill into a following train, head-on. 80 died, many of them children. The killer was the brake's logic. The Smith non-automatic vacuum brake held the shoes on only while the engine actively maintained a vacuum in the train pipe. Let air in, and the brakes released. So when the crew uncoupled and broke the vacuum hose, air rushed in, and every brake on the 10 detached carriages let go. The fail-safe ran backwards. Losing the system meant losing the brakes. What was left to hold them? One handbrake in the rear van, and ballast stones scotched under the 6th carriage's wheels. On the incline, gravity's pull along the slope is F parallel equals mg sine theta, the angle just under a degree, but acting on the full mass of 10 carriages. The starting jolt beat the static grip of the stones. The wheels climbed over them, dumping the whole load onto a single handbrake that never stood a chance. 2 more holes lined up behind it. The carriage doors were locked from the outside against fare dodging, so passengers were trapped inside the runaway. And the line ran on time interval signaling, trains spaced only by the clock, with no way to confirm the track ahead was clear. The following driver got no warning. The response was a landmark, the Regulation of Railways Act of 1889. It made 3 things compulsory across passenger railways. Automatic continuous brakes, where any loss of pressure applies the brakes rather than releasing them. absolute block signaling, one train to a section, and interlocked points and signals, so a route cannot show clear unless it truly is. The 5th of October, 1999, near London Paddington. A three-car Thames train's turbo pulled out, and, at about 8:08, passed signal SN109 on gantry-aided danger, a red, doing around 41 miles an hour. The points routed it across a crossover into the path of an oncoming high-speed train, at a combined closing speed near 130 miles an hour. 31 died. Over 400 were injured. Reconstruct the driver's eye. A low autumn sun sat directly behind the train, and reflected glare lit the inactive yellow lenses so they looked switched on, masking the red beneath. Gantry 8 carried a non-standard, reverse L cluster of signals for several lines at once. Emerging from the shadow of Portobello Bridge into that glare, it was dangerously easy to read the wrong one. There was a last electronic guard, the automatic warning system, but it sounded the same tone for every restrictive aspect, double yellow, single yellow, or red, so drivers learned to cancel it by reflex, without checking the signal. Driver Michael Hodder canceled 3 successive warnings in a matter of seconds and rolled across the crossover into the other train's path. And this was not a fresh trap. Signal SN109 had been passed at danger 8 times in the previous 6 years. The near misses were logged, but Railtrack's fragmented safety culture never redesigned the gantry, never targeted training at the sighting hazard. The warnings were all there, simply unread. Lord Cullen's inquiry reshaped British rail safety. It created the Rail Safety and Standards Board and the Independent Rail Accident Investigation Branch, and drove the rollout of TPWS. Trackside radio loops now measure a train's approach speed, and if it is too fast to stop at a red, they apply the emergency brakes automatically, no driver input required. The 3rd of June, 1998, near the village of Eskede in Lower Saxony. An IC1 train set, the Wilhelm Conrad Röntgen, ran at 200 kilometers an hour. The steel tire of a wheel on the third axle of the leading carriage fractured. It peeled up, speared through the carriage floor, and struck a set of points. The train derailed into the piers of a 300-ton road bridge, which collapsed onto it. 101 died, the deadliest high-speed rail accident in history. The flaw was born of comfort. The original IC wheels were solid monoblock steel, but at speed they wore unevenly and set up a droning resonance in the cabins. So engineers fitted resilient wheels, an inner steel body, a 20mm rubber damping ring, and an outer steel tire. The rubber killed the noise, but removed the rigid web that had kept the tire round. Without that stiff support, the thin tire flexed into a faint ellipse on every rotation. About 500,000 cycles a day at 200 kilometers an hour. A fatigue crack began on the inner bore, where steel met rubber, hidden from visual and eddy current inspection alike. Paris law describes what followed. The rate of crack growth, dA by dN, equals C times delta K to the power M. As the tire wore from about 920 millimeters in diameter down to 862, the wall thinned, the flex rose, delta K spiked, and the crack accelerated until the steel failed in an instant. Then the holes cascaded. A passenger had felt the broken tire pushing up through his armrest and told the conductor, but policy required the conductor to inspect before pulling the emergency brake. Over a minute at full speed before the switches. The bridge, unlike a cantilever, rested on just 2 slim trackside piers. Lose one, and the entire 300-ton span dropped onto the carriages. Deutsche Bahn retired every resilient wheel and went back to forged monoblock steel. Inspection moved to phased array ultrasound and automated wayside acoustic monitoring that can hear a subsurface crack forming. And the replacement bridges were rebuilt as cantilevered, pier-free spans, taking the vulnerable columns out of the danger zone entirely. Put the 4 together and a pattern emerges. Modern rail safety is layered deliberately. Materials science gives us vacuum-degassed forged wheels and ductile steel. Active monitoring listens for cracks with ultrasound and acoustic sensors. Control automation enforces speed through TPWS and ETCS. And passive infrastructure, cantilevered, redundant structures, survives the impact when everything upstream has failed. For independent barriers, so no single hole runs clean through. That is the real lesson of the wreckage. Safety rests on no single component, but on a chain of redundant safeguards, designed so the system fails gracefully. Each of these disasters was paid for in lives, and each one rewrote the rulebook that protects the next train. This has been Learn Railways.